Alright, now thanks for tuning in. Lana will discuss our question 6, a question paper on chemical equilibrium. So in the description below, uzothola ama link for my questions for this question paper. Right, this is 2019 May-June exam. Lana sine equilibrium question on the Kc value. Well, question the balanced equation below represents the reaction used in the Haber process to produce ammonia. So mawuthatha ukubheka la, I have nitrogen in a gaseous phase, and then in a hydrogen in a gaseous phase, and then in a equilibrium sign, and then in the ammonia on the right hand side, and then delta H less than 0. So it means the forward reaction exothermic reaction. So this chemical equation is also balanced. And then but the Haber process to produce ammonia, in industry the product is removed as quickly as it forms. This is important because in industry thina ku-industry bafocus on the production side kakhulu. So in order to maximize their production level, they need to remove ammonia as quickly as possible so that more of your ammonia is being produced kule Haber process. Now 6.1, but you write down the meaning of the double arrow used in the equation above. So lana 6.1 and the double arrow simply means with this inani sine reversible reaction. The double arrow simply means this is a reversible reaction. This is a reversible reaction, or the concentration of the products is the same as the concentration of reactants. Now 6.2 bathi bafunani, give one reason why ammonia is removed from the reaction vessel as quickly as possible. Is to increase the production or the yield of ammonia. So reversible reactions are anama applications wakhona, like we have a process where it produces ammonia. So the minute the ammonia is forming, we need to remove it so that it produces more of the ammonia as quickly as possible. Just like I've mentioned earlier, in industry we are more focused on the production kakhulu. And then now question give below basiphe graph but the graph below shows the percentage yield of ammonia at different temperatures and pressure. Okay, this is a percentage yield of ammonia. Keep in mind we have something as a theoretical value. There's something we call a theoretical value, and then a practical value or the actual value. Like now we conduct an experiment. There's what we call the practical value. Like now conduct the experiment, the exact amount as the calculated amount, right? That's why I see the concept of percentage yield. A percentage yield is simply a value out of the theoretical value, sithola how much when conducting the actual experiment, right? Okay, so we clarify later on during this question. Now 6.3, so pendulum question 3. So on the graph siyabo percentages on the y-axis, and then on the x-axis basipe pressure, and then the curves are represent the different temperatures. Now 6.3, but to write down the percentage yield of ammonia at a temperature of 450 degrees and a pressure of 200. So this is the pressure of 200 asikhuphuka sifuna no 450 degrees. Boom 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 siyaphezulu 450 degrees sifika la siyabo ukuthi the percentage yield is what? Is 20%. Is 20%. This is the percentage yield at these conditions, right? Okay, 6.4. Okay, now 6.4, but he referred to Le Chatelier's principle to explain each of the following deductions made from the graph. 6.4.1, but for a given pressure, in this case the pressure is constant, and then the yield of ammonia at 500 degrees Celsius is much lower than that at 350 degrees Celsius. Atingibale the chemical reaction la. So this is gas, and then it's not 3H2 gas, equilibrium sign or reversible reaction, NH3 gas, right? And then delta H less than 0. Right, the forward reaction represents what? Represents a exothermic reaction, and the reverse reaction is endothermic reaction. So we want to know why the yield of ammonia at a temperature of 500 degrees is much lower than that at 350. So an increase at the temperature move from or increase from 350 to 500, or let me say we are comparing a temperature between 350 and 500, and as we want to understand why the yield at 500 degrees Celsius is lower than the temperature at 350 degrees Celsius. Why is that so? Since the forward reaction is exothermic, ne? Atingibhale phansi, forward reaction is exothermic, and the reverse I think the reverse reaction is endothermic. It simply means that nangabe I'm at a temperature of 500 degrees, it means like now since we compare 350 to 500, it means there's an increase in temperature from 350 to 500, and by increasing the temperature at a higher temperature, I'm actually favoring the endothermic reaction, because according to Le Chatelier, an increase in temperature, the disturbance equilibrium is actually an increase in temperature, but according to Le Chatelier's principle, equilibrium will do what? Will try to counteract that change by decreasing the increased temperature, by decreasing the higher temperature. So therefore the reverse reaction in this case will be favored. So it means again, if we favor the reverse reaction, less of ammonia will be produced. That's why at 500 degrees Celsius we have a lower yield than 350. So basically into bengikhuluma la, the answer for 6.4.1. 6.4.1. So at 500 degrees Celsius, there's going to be a lower yield because an increase in temperature favors the reverse reaction, which is the endothermic reaction. And according to Le Chatelier's principle, what happens? equilibrium will always counteract the change. In this case, it's an increase or a higher temperature. The equilibrium will look to decrease the temperature by favoring endothermic reaction. Right, so ungayibeka ngamagama wakho ke leyo answer for this question. 6.4.2, for a given temperature. Now, temperature is constant. The yield of ammonia at 350 atmospheres is much higher than that at 150 atmospheres. I think ngibhalele equation again. N2 3H2 equilibrium 2NH3, right? And then siyabona ke bheka ke nangabe uzokhuluma ngepressure, if uzosebenzisa if ufuna discuss Le Chatelier's principle around the pressure, you need to look at the number of moles on the left hand side and the number of moles on the right hand side. So bheka ke lana I have 1 mole, lana ngina 3, so the sum gives me 4. So on the left hand side I have a total of 4 moles, and then on the right hand side I have a total of 2 moles. Right, bheka ke for a given temperature, the yield at 350. So the temperature is high, man. I'm comparing with 350, no, 150. So from 150 to 350 is an increase in pressure. So an increase in pressure always favors the side with the least amount of moles. So the forward reaction is always favored whenever there's a higher pressure. So it means the forward reaction is favored and more of ammonia will be produced. So a higher pressure simply means the forward reaction is favored and a higher yield of ammonia will be obtained. So according to Le Chatelier, the forward reaction is always favored, or let me say a higher pressure always favors the forward. A higher pressure favor always the side with the least amount of moles. So now siyaku 6.5. Okay, 6.5 fundeka ngalendlela bathi a technician prepares ammonia by reacting 6 moles of hydrogen gas and 6 moles of nitrogen gas. Now 6.5.1, but calculate the maximum number of moles of ammonia that can be obtained in this reaction. So keyword lana is what? Ilo maximum. No? Want the maximum number of moles of ammonia that can be produced. This funuktola the maximum number of moles of ammonia that can be produced. So as I've mentioned earlier, there's a practical value and a theoretical value. So the maximum number of moles is actually the theoretical value in this case. Right now 6.5.1 activity and okay, I think parallel equation again. All right, N2 plus 3H2 and then 2NH2 3 man 3. So my guess is wonkela. Right, and then siyabona ukuthi from this reaction that 1 mole of nitrogen gas reacts with 3 moles of hydrogen gas to produce 2 moles of ammonia. So these are the ratios of our balanced chemical equation. So thina sifuna ukwazi ke ukuthi what is the maximum amount of omega from the 6 mole of hydrogen gas and the 6 mole of nitrogen. So therefore lana sizodinga understand that which substance or which reactant between nitrogen and hydrogen is actually the limiting reagent, because the limiting reagent is the substance esitshela ukuthi reaction is stopping. right? So in our case, the limiting reagent la kuzoba hydrogen gas, since reactisa 6 moles and 6 moles, and then hydrogen has the highest ratio, uye uzoba limiting reagent. So the 6 moles izosebenza yonke for hydrogen, and then for the 6 moles izosebenza yonke la for hydrogen, and then nitrogen some of it izosebenza. So in other words, it means lana sizoba na the ratios azothi ke wona azothi I'm thinking okay, azothi asiqale ngayo le 6 mole of hydrogen gas, yeah, 6 mole of hydrogen gas azoproduce ngayiki 1/3 of 6, right? And then 1/3 of 6, why ngithi 1/3? Because since ngisebenzisa everything ekhona la ku hydrogen, so the 3 divided by 3 nginikeza ubani u6 because of na 6 moles lana. So ngapha nakhona ngiyodivide ngobani ngo3 again. 1/3, 1 divided by 3 is 1/3. 1/3 times 6 nginikeza ngayiki 2. So it means lana your reactor only 2 moles. Your reactor only 2 moles in nitrogen. Is your reactor na 6 moles of hydrogen to produce 2/3, 2/3 of 6, which is what? 6/3 is 2. 2 times 2 is 4, so it's 4 moles of nitrogen of ammonia will be produced. So therefore ngitheni ekuqaleni react, okay, ngitheni we need to determine limiting reagent kuqala, since initially sinangayiki sireactisa 6 moles and 6 moles of hydrogen and nitrogen. So therefore, since ayafana ama moles wethu, the one with the highest ratio yiyo izoba limiting reagent. So for the limiting reagent ichaza ukuthi everything izoba used up. Yezositshela ukuthi reaction yophela nini, or yeah, yezositshela ukuthi reaction ethi izophela nini. So since kusebenza 6, ngapha kuzosebenza 1/3 of this amount, ngapha kuyofomeka ngayiki 2/3 of this amount. So therefore ama ratios wethu so sisebenzisa stoichiometry to determine the highest number of moles for guys, the maximum number of moles for ammonia. So siya ku 6.5.2. Okay, now 6.5.2, but the above reaction now takes place in a 500 cubic centimeter container at a temperature of 350 and a pressure of 150 atmospheres. The system is allowed to reach equilibrium. Use the graph above and calculate the equilibrium constant Kc for this reaction under these conditions. So lana prepare a table already. So komele into soyenza nje ukupluga in ama values nje. Okay, now 6.5.2 na chemical reaction yethu, and then siyabona ke la ukuthi the initial amount is what? Is 6 and 6 lana for nitrogen and hydrogen in moles, and then the ammonia initial amount is about 0 because reaction rate is right. The mole ratio is 1:3:2, and then lana used formed. So this is the amounts are used and formed for the products, the number of moles at equilibrium, which are 7 to calculate the concentrations, and then volume is given as 500 cubic centimeters, but kumele si convert it to decimeters, so sino 0.5 la, right? And then what else are we given? Basipu 6 for hydrogen, 6 for nitrogen moles. And then lana 6.5.1. So let's calculate the maximum number of moles of ammonia that can be obtained in this reaction. So the value esitole la, it's actually the formed amount because of the ammonia, but there's a catch la. As we like graph it, so what is 7 say the graph above. Let's 7 say the graph above. Okay, so this is the graph. Siyabona ke lana basiphe different temperatures and pressures, and then but there are conditions la, right? Nama condition ubani 350 degrees Celsius and a pressure of 150. We need to determine percentage yield kulama conditions law. Remember, ekuqaleni ngitheni, there's a practical value and a theoretical value. So the technician is conducting an experiment la, or prepare, like it's not an experiment, but to prepare ammonia using a hydrogen and nitrogen. So lana ke theoretically uthini uzothola a maximum number of 4 moles la, but thina asisebenzisi the exact amount or the maximum amount because of these conditions. So kumele sibuyele back kule graph to check 150 temperature, so 150 pressure, now 150 la. This is 150 so this is 150. Temperature is what? It's 350. Siyaqhubeka siyaphezulu sizala. Okay, shukuthi percentage yield ubani 35%. So therefore it means again, simply means ukuthi the formed amount is actually what? The formed amount is actually formed is equal to 35% of the maximum amount, which is 4 moles. So it's 35 over 100%. So calculate it. 35 times 4 is what? Is 1,4. Is 1,4. So let us know 1,4 moles. So the formed number of moles is 1,4, because at these conditions ukufomeka only 35% of the 4 moles according to their graph here to layer. So now since on the products for the formed amount 1.4, at equilibrium the product is about 1,4 as well. So using stoichiometry on this row to find the used amounts for hydrogen or nitrogen, so 70 stoichiometry again. So lana kuyoba 3/3 times 1,4 is equal to what again? Is equal to what? Or you ungafaka x base you cross multiply, then make x a subject of the formula. It's still fine, but ngithanda ukuyisebenza ngale ndlela le, it makes life easier. Times 1,4 equal to 2,1. So lana kuyoba 1/2 times 4. 1,4 is equal to half times 1,4 is equal to 0,7. Since if value like the given value was, or the calculated value kule row leli is 1,4, nangabe ngifuna lamanye ama values lawo where I value yami ikhona, where there's a given value khona. In order to calculate lawa manye, le ratio le above, the ratio above of the given value, you divide ngayo lamanye ama ratio, and then in turn multiplying at the given value, just like I did la. So if like say for instance lana being no 2,7 and then ngifuna lama value angapha nangapha, bengizodivide ngo 3 ngapha, it means bengiba no 1/3 times ngalo 2,7 la, ngapha ngibe no 2/3 times 2,7 bese ngiyothola lama values wala, right? Or you can just do the normal way, or ngale ndlela abayifundisa ngakhona, where since ngifuna i-value yala, I place x, then I cross multiply and find the value for x, ngibuye ngibeke u-x la and cross multiply, getting ngithole ubani u-x. Now the number of moles at equilibrium is 6 subtract 0,7, asibone 6 subtract 0,7 is equal to 5,3, and then lana is 6 subtract 2,1 is what? It's 3,9. 3,9. Now for the concentrations, okay, it's the number of moles at equilibrium, which is 5,3 divided by 0,5. Lana it's 3,9 divided by 0,5. Lana it's 1,4 divided by 0,5. Now let's calculate. You see 5,3 divide 0,5 is equal to 10,6. Lana 10,6, and then 5,3 0,5, and then lana it's 3,9. 3,9 is equal to 7,8. 7,8, and then here 1,5, 1,4. 1,4 equal to 2,8. 2,8. So therefore now we calculate EKC value yethu-ke manje. Senginama concentrations for our reactants as well as the product. Okay, now for the Kc value, Kc is equal to this. Kc is equal to the products over the concentration of the products divided by the product of the concentrations of our reactants. So this is equal to concentration here ammonia, it's 2,8 squared divided by nitrogen 10,6, hydrogen 7,8 cube. This is equal to, let's calculate. What's our calculator? Squared 10,6 times 7,8 cubed is equal to 0. Okay, in 4 decimal places is equal to 0,0016. So no mungayisa ku 3 decimal places. Now uzoyisa ku 3 decimal places izothi 0,002. Kuzodepend ukuthi but the answer yakho ibhale in terms of how many decimal places. So lana mina ngizoyishiya la ku 4 decimal place. Now ufuna ukuyisa ku 3 decimal places uzothi 0,002. So this concludes our video. So thanks for tuning in. Thanks for watching. Nangabe we enjoyed this video, leave a like, leave a thumbs up. Nangabe a question, leave a question in the comment section. Nangabe new to this channel, please consider subscribing. Thanks for watching. Asibona nakulo video ilandelayo. Bye bye.